In this class, we want to look at a transformer. Learning outcome. At the end of this video, you will learn the following: what transformer is all about, types of transformer, efficiency of a transformer, advantages of high voltage in power transmission, uses of transformer. Then we'll solve some problems. Let's look at what transformer is all about. A transformer is a device for stepping up or stepping down an alternating voltage. In one of my videos, we looked at alternating current circuit as well. So you can check that video for more information about alternating voltage. So we said a transformer is a device for stepping up or stepping down an alternating voltage. Let's look at the diagram of a transformer. Transformer is composed of a laminating iron core in which laminating iron core with coil and current entering the first part, alternating voltage here, then it has another part where you have your current, the outlet, and also your voltage. So if you connect this to, let's say, a bulb, it will glow. So this is a circuit diagram of a transformer. Transformer has two parts. We have the secondary part, and the current in the secondary is represented with IS, voltage in the secondary IV. Then it has a primary part too. So a transformer has two parts, the primary coil and the secondary coil. So the current that enters the primary coil is IP. The voltage that enters is VP. So how does a transformer step up or step down? When an alternating voltage, alternating current enter the primary coil, it will be magnetically induced into the secondary coil. In one of our videos, we looked at electromagnetic induction. You can look at it for more information of what electromagnetic induction is all about. So in line with Faraday's law of electromagnetic induction, the current will be induced in the secondary coil. And if a load or resistor is connected here, there will be what? An outlet. So this is how a transformer works. It has two parts, the primary coil, the secondary coil. And according to Faraday's law of electromagnetic induction, the voltage that is induced is equal to the number of turns in the secondary and the magnetic flux in the secondary, the rate of change of the magnetic flux. According to Faraday's law of electromagnetic induction, that whenever there is a change in the magnetic flux linking the circuit, an EMF is induced. And the second law states that the induced EMF is directly proportional to the rate of change of magnetic flux. So we can, to calculate the voltage in the secondary coil, we use this expression. Then the voltage in the primary coil is equally given number of turns in the primary times the rate of change of magnetic flux in the circuit. So we use this to calculate the voltage in the primary and the secondary. So let's call this equation 1. Let's call this equation 2. If we equate equation 1 and 2, if we equate equation 1 and 2, we will have that voltage in the secondary, voltage in the primary is equal to number of turns in the secondary, number of turns in the primary. Let's call this equation 3. If the efficiency of the transformer is 100%, let's assume it's 100%, then we can say that power input is equal to power output. And what is our power? Power is equal to VI. So the voltage in the secondary, current in the secondary is equal to voltage in the primary, current in the primary. If we rearrange this, let's call this equation 4. If we rearrange this, we have voltage in the secondary, voltage in the primary is equal to number of turns in the secondary, number of turns in the primary, which will be equal to current in the primary over current in the secondary. You know from this, if you simplify this, you have voltage secondary, bringing the voltage together, current primary, current secondary. So if this, from here we have voltage secondary, voltage primary is equal to this, and we also have it here. So we can relate these three parameters together. So we call equation 3 transformer equation. We have two types of transformer, the step-up transformer and step-down transformer. How do I know a transformer is step-up and step-down? We have known the relationship between voltage in secondary, voltage in primary. We say it's equal to number of turns in secondary over number of turns in the primary. And we also have the expression for voltage in secondary, voltage in primary. We say it's equal to current in primary over current in secondary. So let's go further. These three parameters, this equation is very, very, very important as far as transformer is concerned. At times, we may be given this three parameters, we have to find the fourth one. At times, we may consider this side. At times, it may just be this. So this expression is very, very important. Next, let's look at types of transformer. Like I said, we have two types of transformer. We have the step-up transformer and step-down transformer. A transformer in which the number of turns in the primary, the number of turns in the secondary is greater than the number of turns in the primary, and the voltage in the secondary is greater than the voltage in the primary. We call such transformer a step-up transformer. While a transformer that the number of turns in the primary is greater than the number of turns in the secondary, and the voltage in the primary is greater than the voltage in the secondary, we call such transformer step-down transformer. Let's represent it diagrammatically. We have a transformer. Let's say this is our transformer. We are looking at the step up. This is our number of turns in the primary. This is the number of turns in the secondary. So a transformer in which the number of turns in the secondary is greater than the number of turns in the primary, and the voltage in the secondary is greater than the voltage in the primary, is called a step-up transformer. So this is the diagram for a step-up transformer. Then for a step-down transformer, we can represent it. Here the number of turns in the primary is greater than the number of turns in the secondary. So this is the step-down transformer. The number of turns here you see is far, far greater than the number of turns here. While the number of turns in the case of step-up is greater than the number of turns in the primary, and the voltage too is greater. So these are the difference between a step-up transformer and a step-down transformer. When do we use a step-up transformer? When do we use a step-down transformer? We use a step-up transformer after generation of electricity. You know electricity is generated. We are looking at AC, and it is AC that can be stepped up. Later we shall be looking at the difference between AC and DC. AC current, alternating current, can be stepped up. It is normally generated using AC generator. The moment is generated based on the design of the generator. The voltage is normally stepped up. We stepped it up for easy transmission and using step-up transformer. And at the point where we want to use it, it is stepped down to a voltage of 240 volts, which is normally used depending on the location. So we use a step-up transformer prior to transmission. Then we use a step-down transformer to reduce the voltage to the ones that we can use at home. So the transformer in our neighborhood, they are called step-down transformer. While the one that we see along a power station, they are step-up transformer. We shall be using this equation as we make progress. Let's look at efficiency of a transformer. Efficiency of a transformer. Efficiency of a transformer. The efficiency of a transformer is defined as the output power to the input power. Mathematically, we can say efficiency output power over input power, and because we are seeing efficiency, it's normally expressed in percent. So this is the expression for efficiency of a transformer. So let's simplify the output power. We have the output voltage. Our power is expressed. Power is equal to VI. So if we use that, we have voltage in the secondary, current in the secondary, over voltage in the primary, current in the primary, times 100. So for a transformer, if I know the output voltage, the output current, the input voltage, the input current, multiplying by 100, one will be able to calculate the efficiency of the transformer. The efficiency of a transformer ideally is not 100%. So let's look at why the efficiency of a transformer is not 100%. Let's look at power losses. Power losses in a transformer, while the efficiency of a transformer is not 100%. One of the ways in which power is lost in a transformer, we call it copper loss. In the copper loss, it has to do with the energy lost in form of heat in the transformer. We have earlier seen that power is expressed as voltage over current, which can be expressed as this. So in the process of transmission, power is lost in the process of transmission. So based on the design of the transformer. So one of the ways in which power is lost, we call it copper loss. The second one is eddy current. And this is concerned with unwanted induced current. I told us earlier that as voltage enters the primary coil, it is induced into the secondary coil. So there are some unwanted current in the process. That unwanted current, we call it eddy current. And it is due to the soft iron core that is being used in the transformer. And to reduce this eddy current in transformer, the coil of transformer is normally laminated. Then the third one is flux linkages. Flux linkage is the third ways in which power is lost in a transformer. And this is energy lost due to linkage of magnetic flux. The magnetic flux that is being induced, the linkage in it, we call it flux linkage. And this flux linkage can be reduced by laminating the air gap in the core of the transformer. So these are the three ways in which the power is lost in the transformer. And by this, the efficiency of a transformer is not 100%. The next thing we want to look at is advantages of high voltage in power transmission. Advantages of high voltage in power transmission. High voltage in power transmission. Power is normally transmitted at high voltage. I told us earlier, when power is being generated using AC generator, it has to be transmitted. But before then, the voltage is stepped up. We say transformer is a device used to step up or step down voltage. So the voltage produced based on the design of the AC generator has to be stepped up for transmission. So we want to look at the advantages involved. Why do we transmit power at high voltage and low current? That is what we want to look at. So the first reason for power to be transmitted, it is transmitted using a line wire. And assuming we are using a very thick wire, a wire that is very thick, from Ohm's law, we have that our current, our voltage is equal to IR. So assuming we are transmitting power at high voltage, at high current, low voltage, you discover that the opposition, you are transmitting power at high current, the opposition from the line, the conductor, will be very high. And it will generate more heat. The power loss will be very, very high. So because of this disadvantage, power is not transmitted using high current, but rather high voltage and low current. So this is one of the reasons why we transmit power at high voltage and low current. Like I say, if you are transmitting power using high current, you need to make the wire very thick, and as the wire is thick, the opposition will be high. So high current multiplied by high opposition, the power lost in the course of transmission will be very high. So because of that, we don't transmit power using high current. Rather, power is transmitted using low current and high voltage. So that is one of the reasons. Then the second one is that we have seen that our power is given as IV, which can be expressed as I square R. Our energy, electrical energy, is power times time. So from here, we'll have this. So if we are transmitting power as high current, like I earlier said, the energy lost will be very high. High current, taking the square of it, the resistance will equally be high because the wire will be thick. So because of this, the energy that is lost is also high. So because of these reasons, power is normally transmitted at high voltage and low current. However, there are also disadvantages transmitting power at high voltage. One, it requires high insulation. High insulator, you need insulator. In power transmission, let's say the power line, some of them you see an insulator, big ones. And even at power station, you see brown ceramic, they are the insulator. So if you are transmitting power at high voltage, you required much insulator. That is one of the disadvantages. Then the other one is that the moment there is power, the moment any of the high tension wire cut, it is very dangerous because of the high voltage. It's very risky. If any of the high tension wire in the course of transmission cut, or any of the pole fell in the course of transmission, the risk involved is very terrible. So because of this, transmitting power using high voltage is good, but there are some risks involved. The next thing we want to look at is uses of transformer. Like we earlier said, transformer is majorly used to step up or step down alternating voltage. And we have seen that we have two of the type, the step up transformer and the step down transformer. Okay, let's solve some example using the equation we earlier derived. Example, we have equation here. A 240 volt AC is applied at the primary coil of a step-down transformer. What is the ratio of the secondary turns to primary turns if the voltage available at the secondary coil is 60 volt? So, to approach a equation like this, we look at the given parameter. We know the voltage at the primary coil. We are given Vs to be 240 volts, Vp to be 60 volts. We have our expression relating the voltage at both primary, secondary to the number of turns at both primary and secondary. So if we substitute, we will have 60 over 240 will be equal to Ns over Np. So if we simplify this, we'll have 1 over 4 ns over np. We are looking for the ratio. Which one says what is the ratio of the secondary turns to the primary turns? So the ratio of the secondary turns to the primary turns will be equal to 1:4. So for this transformer, the ratio of the secondary turns to the primary turn is 1:4. It's a very straightforward question. All we need is what? Our formula. Let's look at another example. Let's look at another example. We have a question here. A transistor radio adapter. Let me take it again. A transistor radio adapter transformer delivers 12 volts to the radio. If the input to the transformer is 110 volts and primary coil contains 400 turns, how many turns are on the 12 volt secondary? Also, to go about it, let's look at the given parameter. We know the number of turns in the primary to be 400 turns. The voltage in the secondary is given 12 volts. The voltage in the primary is given to be 110 volts. So using our transformer equation, Vs over Vp, Ns over Np. We are looking for Ns. So Ns, from here, Ns will be equal to Vs Np over Vp. So if we substitute 12 times 400 over 110, if we simplify, we have 44 turns. So this is the number of turns in the transformer. Let's look at another question that involves the efficiency of the transformer. Another example, a question that involves the efficiency of a transformer. Okay, we have a question here. It says if a 220 volt step down transformer is used for lighting 8 12 volt 20 watt lamps, find the efficiency of the transformer when a current of 1 ampere exists in the primary coil. Let's look at the solution to the question. We know the voltage in the primary to be 220 volts. We know the current in the primary to be 1 amp. Then the output power output is, we can calculate it, is 8 times 20, because from the equation we say that the transformer, the voltage from it is used to lighting 8 12 volt 20 watt lamp. So from here we have that the power output is given as this. Then let's look at power input. The power input is equal to Vp times Ip. So we have 220 times 1, which will be equal to 220. Then the efficiency of the transformer now, we say is output power output over power input times 100. So if we substitute, the power output is 160, the power input is 220 times 100. So the efficiency of the transformer, if we simplify, is 72.73%. So the efficiency of this transformer is 72.73%. So this is the approach that we use in computation, calculating either the number of turns, the voltage in primary, secondary, and even the efficiency of the transformer. Thank you very much for your attention. Please subscribe to this channel and like and share this video.